H with a 0. That's going like this. That spin of the nucleus of the proton can be aligned parallel to the magnetic field or anti-parallel like this. And it has a spin of 1/2. We have something called the nuclear magnetic spin I is equal to 1/2. And then m sub I, which is the spin along the magnetic field, can take the values of 1/2 or minus 1/2. And that would correspond to the spin up or the spin down, okay? Now, the interaction of this magnetic dipole moment with the magnetic field is the following. The energy, E, is equal, as you know, to Planck's constant times the frequency, and that is going to be equal to what we call the dipole moment of the dipole moment of the nucleus in question, dotted into the the vector of the magnetic field. Now, you've already noticed that I'm having to introduce vector quantities. If you haven't had this, don't worry about it. I'll just develop it and we'll get some final equations. But both the magnetic moment, which is what these little arrows represent of the nucleus, and the overall magnetic field is a vector. And to get the energy of the interaction of that dipole moment with the magnetic field, you have to take what is called the dot product between the vector for the magnetic field times the vector of the dipole moment. We then have the relationship that this dipole moment is equal to something called the gyromagnetic ratio, which is a constant for each nucleus, times Planck's constant divided by 2 pi, that little slash means we divide it by 2 pi, times the spin of the nucleus, I, that I've introduced down here, okay? Let me just indicate down here that H with a slash in it is Planck's constant divided by 2 pi, okay? And from this, we can determine that the frequency of the NMR experiment is going to be equal to the gyromagnetic ratio times the magnetic field divided by 2 pi, okay? Now, let's talk about what this looks like. Here is the energy of that magnetic moment by itself without any magnetic field. Here is H0, it's equal to 0, okay? Now, when we add a magnetic field, put the molecule in a magnetic field, we split the energy, and this is going to be m sub I is equal to plus 1 half, I forgot the half in there. This is m sub I is equal to minus 1 half. And so this is going to be like the spin down, the spin up, okay? And now the transition that we have in the NMR experiment, which has this energy, energy E, is equal to h mu, that is going to be the difference. And because one state is plus 1 half, the other state is minus 1 half, the difference in energy here is 1 unit. 1 half plus minus a half, so that's 1 unit. So that's your basic proton experiment, okay? And it turns out that this dot product here is not a problem because we align the nuclear spin along that laboratory magnetic field. Okay, are there any questions on that before I go on? Okay.